I'm going to show you how we use the definition of an improper integral to actually calculate an improper integral. So let's calculate the integral from 1 to infinity of 1 over x cubed. And let's be clear on what this function looks like. You should know what this type of function looks like, but let me just draw it. This is going to look sort of like this. It looks a little bit like y equals 1 over x, but it actually since x cubed grows much faster than just x does, this descends toward the axis much faster than just 1 over x, but it has a similar shape. So what I'm doing here is I'm going to put in the number 1, and let's choose a different color. It looks good that way. So what I'm doing is I'm finding this area. And keep in mind, even though it looks like this, like the area never gets to, like the curve never gets to 0 the way I've drawn it, it's just going to keep getting lower and lower and lower and eventually actually not eventually get to the x-axis, but it's going to keep getting closer and closer and closer to the x-axis. So let's use the definition to calculate this integral. We're thereby finding the pink area. So the integral from 1 to infinity of 1 over x cubed is by definition equal to the limit as b approaches infinity of the integral from 1 to b of dx over x cubed. Now, it's going to be a little easier to calculate the integral if I rewrite that. This limit as b approaches infinity of the integral from 1 to b of x to the negative 3 dx. That's going to equal the limit as b approaches infinity. Now is where I'm going to find an antiderivative, because note that I just want to note here, this expression is just a regular definite integral, kind that you all know. All I'm doing is I'm just integrating a power function at this point on the finite interval 1 to b. Pretend that this limit as b approaches infinity is not here and that b is just a number. Then this is just a regular ordinary integral that you've seen many times. So this is now going to be limit as b approaches infinity. I'm ready to find an antiderivative. This is going to be, keep the blue color, x to the negative 2 over negative 2 from 1 to b. So that's going to be the limit as b approaches infinity of, it's going to be negative 1 over 2x squared from 1 to b. So that's going to be the limit as b approaches infinity. I'm ready to plug in 1 and b. It's going to be negative 1 over 2b squared minus negative 1 over 2 times 1 squared. In other words, I'm just plugging in the limits of integration. So that's now going to be the limit as b approaches infinity of, actually I don't need the limit, I can actually substitute now. So we see that as b approaches infinity, that first term is going to be like negative 1 over 2 times infinity squared. We wouldn't let you do this in Calc 1. We wouldn't let you write like something over infinity because it's not a number, but you've all done these sorts of limits, so we can use this shorthand. So it's going to be negative 1 over 2 times infinity, and this is going to be minus 1 over 2, because 1 squared is just 1. So that's going to equal 1 over infinity is just 0, so that's going to be 0 minus negative 1 half, which equals 1 half. Now the interesting thing is that what I'm saying here is that this area, despite the fact that it's of infinite width, is 1 half. It's kind of remarkable that we can have an infinite width area and still get, we can have an infinite width region and still get a finite area, but the numbers don't really lie. Unless you find any fault in the calculation that I've done, this should demonstrate to you that that region in fact does have a finite area.